All right, so we're going to go ahead and finish working our way through this problem. All right, we have a runner that starts from rest, accelerates up to her top speed, and at some point, which is not specified, she's reached her top speed and she finishes the race at that speed, and the race total is 100 meters. Right. So we've already gone through the first part of this slide where we're going to break it into two problems. We say the first half of the problem is where she's accelerating at a constant acceleration, and the second half of the problem is once she's reached her maximum velocity, she runs the rest of the race at constant velocity, meaning zero acceleration. And so we'll solve those two problems independently and then link them up together. So we can break it into two problems, accelerating from rest and running at constant top speed. So what we're going to do is we're going to realize that what we're trying to do is we're calculating time, right? So we want to calculate how long it takes her to accelerate from 0 to 15. That'll give us the first time period. And then we need the second time period. But in order to get that, we're going to need to calculate how far she gets during that acceleration period so that we know how much left there is of the race there is to run. Right? So we can determine how much further she has to run at her top speed if we know how far she's gotten in getting up to her top speed. And then finally, we can calculate the time that it'll take to run that distance at that constant speed. Now, this isn't the only way that you can attack this problem, but for now, we'll focus on the strategy. Okay, so part A, let's determine how long it takes this sprinter to accelerate from 0 to 15 meters per second. Right, and we're going to want to use one of our kinematic equations. Right, so we've listed all four here. And our goal is to, we have to determine which one's most relevant, right? So let's be goal-oriented again, right? The goal of our first portion is to determine the duration or the time for her to get up to top speed. And we were given the acceleration rate and the initial and final velocities, right? She goes from rest to 15 meters per second. So since we're trying to solve for time, we're going to eliminate any equation that doesn't have time in it because, if it's not there, we can't solve for it, right? We can't end up with an equation that gives us time if it's just not a variable in the equation. So that eliminates this fourth equation right here. Then we're going to eliminate equations that require position because they don't tell us the final position, right? We start at some point and they don't tell us how far she's gone by the time she reaches top speed. So for now, we're going to tentatively eliminate these guys. Maybe it will turn out that the other equation doesn't work for us either, and that means that we'd have to come back and tackle this, and we'd have to somehow turn it into a two-step problem where we have to find the final position somehow, right? But for now, since we have another option, let's pseudo-eliminate these two guys. And that just leaves this first kinematic equation, which tells us that the final velocity is the initial velocity plus the acceleration times the duration over which she was accelerating. What we can do is we can take that equation, right, and solve it for the thing we're interested in, time, and see if we have everything we need. Right? So taking that equation, rewriting it in terms so that we have the duration by itself. The duration for this part A of the experiment, of this race, right, the part where she's getting up to top speed, is going to be V final minus V initial divided by A, right, where, again, delta T A is the time required to get from rest up to the 15 meters per second of top speed. So we'll hold on to that equation. Next, we're going to find the displacement of how far, right? Oh, I should go back and say this is now solved, right, because they gave us the final velocity, top speed of 15. They gave us the initial velocity. She started from rest. And they give us the acceleration, which is 2.5 meters per second squared. Right? So in essence, we have delta t. We just have to plug in numbers. But we're going to leave it in terms of equations for a moment. So our next step is to determine how far she gets during this acceleration period. Right? So now we're solving for displacement. And we have the acceleration given, 2.5 meters per second squared. We have the final velocity and the initial velocity. And now we actually have the time, right? We just said we've gotten delta t for the first leg of the race. and it's all in terms of known variables. So if we plug the numbers in, we can get a numerical value for the time, the duration of the first part. So let's go and look at what equations we have. Again, the four tools that we have are the four kinematic equations. Again, we're going to eliminate any equation that doesn't have the thing that we're trying to solve for. And this time it's displacement. So this equation has no x final, x initial, delta x. So that's out of the question. With the amount of information we have, because now we have added time as something that we've now solved for, any of the other three equations will work. So let's go ahead and just pick one, right? I'm going to pick the simplest one. This may not look like the simplest, but it has, everything is linear. There's no t squareds or v squareds. Everything's just v, t, and x. All right, so let's try this one. So we take that equation that we just circled, and let's solve it for the displacement, right? Displacement is final minus initial position. So we bring the initial position over to this side, and we get displacement is equal to initial velocity plus final velocity over 2 times the duration in time, right? And since this is interested in how far she gets in that first leg of the race, we'll put in the time for that first leg of the race, right? So now we're just going to plug in numbers, right? Delta TA is VF minus VI over A, so that's 15 meters per second top speed minus rest divided by her given acceleration, and that gives us 6.0 seconds is how long it took her to get to that top speed. How far does she get in that time? Well, if we know the final velocity and the initial velocity, which we do, and we now know how long she accelerates for, then we can plug our numbers in. 15 plus 0 over 2 times 6 gives us 45 meters. So in 6 seconds, she gets up to her top speed, and by that time, she's covered 45 meters. So now we can solve part B. To finish the race, she's going to be running at her top speed at a constant velocity of 15 meters per second. And because she's at a constant velocity, by definition, there's no acceleration. So V final is equal to V initial. So we can just call that V. We can drop the subscripts because all the V's are the same for the second part of the race, because she's at constant speed. And we've already found that it took her 45 meters of running to get to her top speed. So the amount of running left, the amount of distance left to cover, is just that 100-meter dash minus the fact that she's already covered 45 meters, and we get 55 meters left to run. Right? Now for zero acceleration, right, because we've just noted that in part B, she's at constant velocity, there's no acceleration, A is 0. So our kinematic equations simplify, right? If A is 0, then V final is VI, right? A is 0 here, V final squared is VI squared, right? V initial squared. Okay, that doesn't really tell us much. That's basically the definition of no acceleration, right? This one didn't have acceleration in it in the first place, so it doesn't drop any terms. But what we can do is we can say V initial and V final, we know that's the same thing, right? We say we'll take this result and plug it into here. This just becomes 2VI or 2V whatever, right? But 1/2 of 2V is just V. So then we have final position is initial position plus just VT, right? You can choose any V because they're all the same. So for this second leg of the race, we have final position is initial position times velocity times time. That's also what we get with this third equation, right? XF is equal to XI plus V delta T, and this term drops out because there's an A here that we're setting to 0 because we know we don't accelerate. These, you notice, are exactly the same equation. And so let's go ahead and use that simplified equation for the second half of the race where there's no acceleration, right? It's just X is equal to VT. It's very, very simple, right? All right, so again, what we are solving for is time, right? We want to know how long it takes her to finish the second half of the race because we already know how long it takes her to complete that first leg where she's getting up to top speed. So we're solving for time. So we rewrite this in terms of time, delta X over V, right? Bring the V over to the other side. This is what we get when we have 0 acceleration. And now we take that equation and we can plug in our specific values. Right here, we're going to take delta x for the second leg divided by the velocity of that second leg, which gives us 55 meters, right? 100 minus 45 means there was 55 meters left to run. And her top speed is 15 meters per second, as stated, which means the second leg of that race is run in 3.667 seconds. So finally, the total time for her race will be the time for the first half plus the time for the second half, which gives us 9.667 seconds, which we round to 2 sig figs as 9.7 seconds.